The infinite square well, we discussed that our particle was trapped in a box where v equals 0 inside the box and v was infinity, or v tends to infinity, outside of the box. In this simple harmonic oscillator case, we're going to analyze the wave function of our particle experiencing a potential v that is a function of position, meaning that the potential of our particle changes with x. If x0 is a local minimum, then we're interested in analyzing the wave function of our particle around that approximated parabola. Classically, in the simple harmonic motion, we had a massless spring with a spring constant k, and the total potential of our system, v of x, was 1/2 k x squared. But the quantum problem is to solve the Schrodinger equation with the potential equals 1/2 m omega squared x squared, where omega is the angular frequency. So let's rewrite the Schrodinger equation, and the Schrodinger equation kind of becomes or looks like this. So there's basically two ways of solving this Schrodinger equation. One is the algebraic way, and the other one is the analytical way. In both the cases, the energy eigenstates, or the allowed energies of your particle, are E sub n being equal to n plus 1/2 times h bar omega. This is the case in both algebraic and the analytic method. And for your wave function solutions, one method uses the Hermite polynomials, and the other method, which is the algebraic method, uses ladder operators. So let's touch on the analytic way first. So for the analytic way, this, just as I said, uses the concept of Hermite polynomials, and the general solution psi sub n is equal to the following, which is m omega all over pi h bar raised to the power 1/4 times 1 over the square root of 2n times n factorial times the nth Hermite polynomial, which is a function of psi, or should I say xi, forgive me for my bad pronunciation, times e to the negative xi squared all over 2, where xi is equal to m omega all over pi h bar, m omega all over h bar, the square root of this, times x. This is the analytic method. In the algebraic method, we use the concept of ladder operators. The general solution psi sub n, which is a function of x, is basically 1 over the square root of n factorial times a plus raised to the power n psi sub 0. Oh, I forgot to mention that your n values, n belongs to real numbers, which means that this belongs to 0, 1, 2, dot, 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 up until whatever you want to. All right, so psi sub n is basically this, where psi 0, this over here, I should use a different ink, this over here is the ground state. The ground state, which has energy E sub 0. E sub 0 is equal to 1/2 h bar omega. All right, so this is what you got for your algebraic solution. I should also explicitly mention that in the case of the analytic method, h sub n represent the Hermite polynomials, and you can look them up on the internet whenever you want to. And for the case of the algebraic method, a plus is the raising ladder operator. And there's also another operator which is called the lowering ladder operator. So what are these ladder operators? This is what we are going to deal with right now. So what are ladder operators? Well, the function of ladder operators is what we're going to discuss. When applied to a wave function of a particle in any given energy state of sub n, ladder operators return the wave function of the particle in its next energy state, either of n or n minus 1, accompanied with a constant. Mathematically, let's look at what actually happens. So we discussed that A plus was the raising ladder operator, the raising ladder operator, which means it has something to do with raising. So when you apply A plus, which is the raising operator, ladder operator, to psi sub n, any given wave function with energy n, it will return the square root of n plus 1 times psi sub n plus 1. And A minus is what we called our lowering ladder operator. So when A minus is applied to psi sub n, I should write down psi sub n plus 1, and this will be made clearer after I write down the whole thing. When applied to psi sub n plus 1, this returns a value of n plus 1 times psi sub n. Now, why did I choose to write down psi sub n plus 1? This is because when we discuss the allowed energies of your particle, we said that n belonged to the reals, right? N was real numbers. And the least possible value of n that can be applied over here is 0, right? So when n is equal to 0, this psi sub n plus 1 becomes psi 1, and you get psi sub 0. That is why we chose to write down psi n plus 1 over here. And this is basically what your ladder operators do. And explicitly mentioning this is the case for the simple harmonic oscillator. And there's more to discuss with ladder operators about how their commutation, the canonical commutation relationship goes in between these ladder operators, and how you could write down the Hamiltonian of the simple harmonic oscillator in terms of these. But we will discuss this in the next video. But for now, that's all.